Welcome tight. Today we're diving into something that might sound a little, intimidating at first.
Oh,
Mathematical problem-solving strategies.
okay.
But trust me, this deep dive is going to be anything but dry.
Oh, right.
We're going to be exploring some truly elegant techniques from Arthur Engel's book, Problem-Solving Strategies.
Oh, yes.
Now, you're probably interested in getting to the heart of these strategies quickly,
Right.
and that's exactly what we're going to do.
Perfect.
So, without further ado, let's just jump right in.
It's fascinating how Engels manages to distill these complex ideas into clear, applicable principles. He doesn't just throw equations at you.
Right.
He provides a framework for approaching problems in a whole new way.
Absolutely. The book's often used for Olympiad training,
Right.
but the strategies themselves,
Yeah.
they're applicable far beyond competition math.
That's what's so exciting. Let's start with the invariance principle.
Okay.
It's all about looking for aspects of a problem that remain constant, even when other elements are changing.
Okay, so it's kind of like finding the eye of the storm. Everything's swirling around, but the center is still...
That's a great analogy. A classic example is the Parliament of Sicilia problem from the book.
Okay.
It's about minimizing conflict by dividing parliament members into two houses,
Okay.
given that each member has at most 3 enemies.
So how does invariance help us solve that? It seems like there'd be so many ways to arrange them.
That's where the brilliance of the principle comes in.
Okay.
Imagine starting with a random arrangement.
Okay.
The invariant here is the total number of enemy pairs within each house.
Okay.
By focusing on members with 2 or more enemies in their current house and strategically switching them,
Okay.
we can reduce that number.
Ah, I see. So each switch brings us closer to the most peaceful arrangement,
Exactly.
where conflict is minimized.
Yes.
We're essentially using the invariant, the number of enemy pairs, as a guide.
Precisely. Engel then takes it a step further,
Okay.
illustrating how zeroing in on a specific invariant can unlock a problem structure.
Okay.
He uses the example of a sequence of points in the plane. Even if the points themselves are shifting,
Right.
focusing on their distance from the origin,
Right.
which could remain constant, might reveal a pattern that helps you crack the problem.
So we're not just looking for any invariant,
Right.
but what gives us the most leverage.
Exactly. The key is choosing the right invariant for the task.
Okay.
And once you've identified it, it can be like shining a light on the problem's hidden structure.
This is already making me think differently about problem solving. But I have to ask,
Go ahead.
are there problems where finding that key invariant is really tricky?
Absolutely.
Okay.
Engel talks about a problem E6
Okay.
involving complex sequences where finding the right invariant is the crux of the solution.
Wow.
And it gets even more interesting when we see invariants pop up in areas like number theory,
Okay.
like in problem E7.
Interesting.
It's a versatile tool.
So tight, if you're ever wrestling with a complex problem,
Yes.
especially one with changing elements, remember to ask yourself, what stays the same? That might be your key to unlocking the solution using the invariance principle.
Good advice.
Now, how about we shift gears and explore a principle that takes a totally different approach?
The invariance principle is all about finding stability amidst change, but
Right.
what if we're dealing with situations where our choices are limited?
Okay.
That's where the pigeonhole principle sweeps in.
Okay.
And it's a surprisingly intuitive idea.
This is the one with the pigeons, right? It always feels a bit like a magic trick to me.
It does have that elegant simplicity. Imagine you have more pigeons than pigeonholes.
Okay.
It's impossible to put each pigeon in a hole without at least one hole having more than one pigeon.
Makes sense. You can't magically create more space just because you need it.
Right.
But how does this seemingly obvious idea help us solve mathematical problems?
Well, think about it in terms of finite sets and limited options. Engel uses a clever example in problem E10,
Okay.
where the challenge is to find a power of a prime number, let's say 7,
Okay.
that ends in a specific sequence of digits like 001.
So we're trying to find some power of 7 that when written out ends with those 3 digits. That sounds like searching for a needle in a haystack.
It might seem that way,
Yeah.
but the pigeonhole principle provides an ingenious solution.
Okay.
You look at the remainders when you divide successive powers of 7 by 1000, our desired ending number.
Okay.
There are only so many possible remainders you can get.
So eventually we're going to run out of unique remainders. We'll have more powers of 7 than possible remainders,
Right.
creating our pigeonhole situation.
Exactly. That means at least 2 powers of 7 must share the same remainder when divided by 1000.
Okay.
And that's the key.
Right.
If their remainders are the same,
Yeah.
their difference must be perfectly divisible by 1000.
Meaning one of those powers has to end in 001. It's like the problem solves itself once we set up the right conditions using the pigeonhole principle.
The beauty is that it's not limited to number theory.
Right.
Think of a group of people.
Okay.
If you have more people than months in a year,
Uh-huh.
the pigeonhole principle guarantees at least 2 people share a birthday month.
So it's a way of proving something must exist,
Yeah,
even if we can't pinpoint exactly what it is. That's pretty powerful.
absolutely. Now, shifting gears a bit, Engel also explores the extremal principle,
Okay.
sometimes called the variational method.
Okay.
This one's all about pushing things to their limits.
Okay, so instead of looking for what stays the same, we're looking for the most extreme cases, the biggest, smallest, farthest, or closest.
Precisely. It's
Okay.
about gaining insight by examining those boundary cases.
Okay.
A great illustration is problem E5, which deals with an infinite set of midpoints in a plane.
Okay.
It states that every point in the set is the midpoint of two other points in the set.
It sounds a bit paradoxical. How can a set have an infinite number of midpoints?
That's where the extremal principle helps us.
Oh.
Let's assume for a moment that the set is finite.
All right.
If it's finite, there must be a point that's farthest from all the others.
Okay.
An extremal point.
But if it's a midpoint, there has to be another point even farther out, right? That contradicts our initial assumption.
Exactly. That contradiction forces us to conclude that our initial assumption of a finite set must be wrong.
Okay.
Therefore, the set must be infinite.
So by pushing the problem to its limit,
Yes.
by considering that extremal point, we unveil a truth that might have been hidden otherwise.
That's the power of the extremal principle. It's especially useful for existence proofs, demonstrating that a solution exists without necessarily providing a method to find it.
Okay.
Engel provides another example.
Okay.
Problem E16,
All right.
about circles of convex polygons, where this principle simplifies what might seem like a complex geometric puzzle.
It feels like we're building up a mental toolkit for tackling all sorts of problems.
That's the point.
Yeah.
These principles are more about a way of thinking than memorizing formulas.
So it's more about adaptability and recognizing patterns?
Precisely.
Okay, cool.
It's about thinking creatively, not being afraid to experiment, and letting the problem guide you toward the best approach.
This deep dive has definitely changed how I approach problem solving. And speaking of challenges, Engel mentions an unsolved problem in his book that I think would be perfect for our listeners to ponder.
He touches on the idea of counting by bijection. It's a bit like
Okay.
pairing socks to make sure you have a complete set. You match up elements from two different sets to figure out how many are in one of them.
So it's about finding a clever way to connect two seemingly unrelated things.
Exactly. And that connection can reveal hidden information.
Okay.
He uses an example of dividing an n-gon with diagonals.
Mm-hmm.
And the way he uses biperson to solve it is really neat.
It's fascinating how these seemingly simple ideas can be applied to such diverse problems.
And then there's counting the same objects in two different ways. This can lead to what mathematicians call combinatorial identities,
Okay.
which are like equations that show two different ways to count the same thing,
Mhm.
often revealing hidden relationships.
I love that. It's like looking at a sculpture from multiple angles to understand its full shape.
And remember, the key takeaway here is that there's no one-size-fits-all solution.
Right.
The real skill is in choosing the right strategy for the right problem.
Okay.
It's about understanding the problem structure and finding the tool that fits.
So, Ty, we've explored the invariance principle, the extremal principle, the pigeonhole principle, and even got a glimpse of some bonus strategies.
Right.
What's the big takeaway from all of this?
These principles aren't about memorizing formulas or rigid steps.
Right.
They're about cultivating a problem-solving mindset.
So it's more about adaptability and recognizing patterns.
Precisely.
Yeah.
It's about thinking creatively, not being afraid to experiment, and letting the problem guide you toward the best approach.
This deep dive has definitely changed how I approach problem solving. And speaking of challenges, Engel mentions an unsolved problem in his book that I think would be perfect for our listeners to ponder.
Oh, really?
Yeah. It's called the Frobenius problem.
Okay.
And it asks, given a set of positive integers that have no common divisor other than 1, what's the largest number that can't be expressed as a sum of multiples of those integers?
That's a good one.
Yeah, even for a set of just 3 numbers. The solution isn't straightforward.
Right.
There's no easy formula to plug in. So
Right.
your challenge, should you choose to accept it, is this.
All right.
Can you find a pattern for this largest unrepresentable number? It's a tough one, but maybe you'll uncover a new problem-solving strategy along the way.
I like it.
Keep that curiosity burning tight. The world of problem-solving is full of endless possibilities.
Absolutely.
Keep on deep diving.